99% accurate. This means that the probability of testing positive when you have the disease is 0.99, and the probability of testing negative when you don't have the disease is also 0.99. This disease is rare with a prevalence of 1 in 10,000 people, so the probability of having the disease is 0.0001. The probability of not having the disease is 0.9999. Probability of testing positive given that you have the disease 0.99. Probability of testing positive given that you don't have the disease is 0.01. Probability of having the disease 0.0001. Probability of not having the disease 0.9999. Here we apply bias theorem to our question. This is formula. We have already determined the required values here. After doing all the calculations, the result is 0.0098. Begin with the formula for the covariance between x and y. Expand the expression for the covariance using the linearity of expectation. Expectation x, y, and expectation x, expectation y using the law of total expectation we calculate. So we find that expectation xy is equal to expected value of the square of x, which is expectation x power 2. We have the values of expectation x, y, and expectation x, expectation y. Substitute these results back into the expanded expression for the covariance. This shows that the covariance between x and y is equal to difference between the expected value of x squared and the square of the expected value x. The expected value of the squared difference between x and its expected value is exactly the same as the covariance between x and y. Xy is equal to 0. Expectation xy is equal to expectation x, expectation y by separating the summation. We can substitute this result into the formula for covariance. When you make the necessary substitutions in the equation, the answer turns out to be 0. Nu is that mean sigma power of 2 is that mean variance. X be a random variable following a normal distribution, and we have another random variable y defined as ax plus b. The mean of y is expectation y is equal to a expectation x plus b is is equal to 0. This final equation. The variance of y is a power of 2 variance x is equal to 1. A power of 2 and variance is equal to 1. As a result of these operations, we have two equations. This is how we find A and B. I cannot explain this process in detail. We have matrix A and vector C defined as to calculate AC. We perform matrix multiplication. We multiply each row of A by the corresponding element in C and sum the results. The first row A 0 to 4 is multiplied by for the first element of C 1 and summed, resulting in 6. The second row of A 2 4 2 is multiplied by the second element of C1 and summed, result 8. The third row of A 3 3 1 is multiplied by the C third element of C1 and summed, resulting in 7. AC is given by the column vector 6 8 7. Firstly, we import the NumPy library and then we define matrix A. We need to calculate the inverse of the matrix A. I use mp.lineage to do this. With this code, we find the answer to question A of the question 9. We will get the output like this. Here are the codes required for question B of the question 9. We need to multiply matrix B by the inverse of the matrix A. We do this with the mp dot function. Similarly, here we need to multiply matrix I by matrix C. We get the outputs of the codes this way. Here are the outputs.